Hello, so we are back again with the session on vector algebra, and in the last class we had talked about scalar product of two vectors. In fact, we had told in the last class that when we talk about product of two vectors, we can define that in two different ways. One is the scalar product or dot product, and the second one is the vector product or cross product. The scalar product we had defined thoroughly in the last class, and today we will start with the vector product. Now for a second, for recapitulation, what was the scalar product? If we have two vectors A and B, then the scalar product or dot product A dot B is given by the product of the magnitude of the vectors A and B and cosine theta, where theta is the smallest angle between A and B. Now let us see how do we define vector product or cross product. And as the name suggests, we will of course expect that now the result of the multiplication of the two vectors will be a vector quantity. Okay, so now for two non-zero vectors A and B, the cross product is defined by this equation. We write it as A cross B, and this is now again the product of the magnitude of the vectors at now sine theta. In scalar product we had cos theta, now it is sine theta, where theta is again the angle between the two vectors A and B, and we have an extra entity over here, n cap. This n cap is the unit vector perpendicular to both A and B, such that AB and n form our right-handed system. So what we mean by that actually, so if we have two vectors A and B, where the angle between them is theta in the anticlockwise direction, and n, as we have mentioned here, is a vector perpendicular to both A and B, or we can say that it is perpendicular to the plane containing A and B, but the direction should be such that A, B and n form a right-handed system. And what we mean by a right-handed system, for this let us come to this figure. So if we have a right-handed screw like this, where this is the x-axis, y-axis and z-axis, and if we move from x to y in the anti-clockwise direction, then the right-handed screw will move along the positive z direction. So here also, if we are moving from A to B, the direction of n should point upward, like the direction in which the right-handed screw will move. So that is what we mean by a right-handed system. Mind it, we can have actually two vectors perpendicular to A and B. One is this n cap and other is the minus n cap. But because we want it to be a right-handed system, so we take this n cap which points upward. So once again, to summarize, the cross product of the vectors A and B, that is the product of their magnitudes multiplied with sine theta and multiplied with a unit vector n. Okay, and now if any of the A and B were 0, what do we do? Now if any of the A and B were 0, actually then theta will not be defined, because we cannot, if say A is 0, A vector is 0, so that means it's a vector with 0 length. We cannot draw it, and therefore the theta angle will also be not defined. So in that case, we define this A cross B as the null vector or 0 vector. In fact, if you remember, for scalar product also we had defined similarly that if one of the vectors are 0, then the scalar product was also defined as 0. Okay, so now we will take some few observations on this definition of vector product. And the first one is the very obvious one, that A cross B or the cross product or the vector product is a vector quantity. And I think that is very much clear from our definition, because the definition here in the right hand side includes this unit vector. So of course A cross B is a vector quantity. Now the second one, if suppose A and B are two non-zero vectors, then can it happen that the cross product is 0? Let us think a little while. When can it happen? Now, if the cross product 0 for non-zero vectors, then it can only happen if sine theta is 0. And sine theta is 0 means theta is 0. So that means A and B are parallel or collinear to each other. So we denote it like this, that A cross B equal to the 0 vector if and only if A is parallel to B. Of course, we are talking about non-zero vectors. And in particular, if B is equal to A, that means if we are talking about A cross A, then that is going to be 0. And it's obvious because in this case, theta is 0. Now, if we talk about if B is equal to minus A cross minus A, then also it will be 0. And see that in this case, theta is going to be pi or 180 degrees. So sine theta is also 0 in this case. Now next, what happens if we have perpendicular vectors, or rather theta equal to pi by 2? For perpendicular vectors, the cross product A cross B will be given by mod A mod B and just the unit vector n, because in this case sine theta is going to be 1. Now point number 4, in view of the observations 2 and 3, we have some two important results basically for the mutually perpendicular unit vectors I, j and k. I hope we remember that we had denoted this I, j, k as the unit vectors along the coordinate axis. Okay, so now I cross I, what is that? If we go back to your result 2, you see that A cross A is 0 vector. So of course I cross I or j cross j, k cross k all will be null vectors. And at this moment, let us remember what was I dot I, j dot j, k dot k, they were all 1. And now I cross j, what is that? I cross j. Now we see that I and j are perpendicular vectors. So that means theta is pi by 2. So we use now rule number 3. And so I cross j will give us, say, mod I mod j. But these are unit vectors. So we will just have a unit vector perpendicular to this I and j. And what is that? That's obviously k, because I, j, k, all three are mutually perpendicular. So I cross j is k. With the same logic, j cross k is going to be I, because I is now the vector which is perpendicular to both j and k. And similarly, k cross I is going to be j. Okay, and the last one in this list, see that now from the definition of the vector product, the angle between the two vectors, theta, can be obtained from this expression. Sine theta is equal to now modulus of A cross B divided by mod A mod B, or rather theta will be given by sine inverse modulus of A cross B by mod A mod B. And see that this A cross B is a vector, so that is why we need this modulus in the numerator. If you remember at this moment, we also had a formula like this, which was theta equal to cos inverse A dot B by mod A mod B from the scalar product. Okay, we continue now with some properties of vector product. And the first one is a very important and interesting one, that vector product is non-commutative. Now, if you remember till now, all the properties of different cases what we have learned, like vector addition was commutative, multiplication of a vector by a scalar was commutative, even scalar product was commutative, but now the first time vector product is non-commutative. In fact, it follows the anti-commutative law. So non-commutative means we can say that A cross B is not equal to B cross A. That means now we cannot play around by changing the positions. And in particular, as I have told, this is anti-commutative. So A cross B is equal to minus B cross A. Why is it so? That will be clear if we look into this figure. Now say A and B are the two vectors and theta is the angle, as usual in the anti-clockwise direction. So now in is the vector which is perpendicular to both A and B and in the direction in which the right-handed screw moves. This we have discussed just now. Now see, if we wanted to calculate B cross A, so now we are moving from B to A. So theta is now directed in the clockwise direction. So therefore, the direction of N is no longer upward, but it will be now downward. That means it is this N1, it is now shown as N1. So this is of course the opposite vector of N. So we have a minus sign now. So A cross B is equal to minus B cross A. Okay, the next property we will talk about distributive laws. So suppose that A, B, C are three vectors, then A cross B plus C is equal to A cross B plus A cross C. That means if we first add the two vectors and then multiply, that is same as if we had multiplied individually A cross B and A cross C and added, we get the same result. The next one, B plus C cross A, that is equal to B cross A plus C cross A. Now mind it, 1 and 2 are not same because this is A cross B plus C and this is B plus C cross A. And we know that vector product is not commutative, so they actually give you different results. And the third property, associativity with scalar. So now if we have two vectors A and B and the scalar lambda, lambda A cross B, this is equal to A cross lambda B is equal to lambda A cross B. So see that the scalar lambda can take any position. We can play around with the position of lambda. It can be outside or it can be with A, it can be with B, or it can be outside both A and B. But mind it, we should not change the order of A and B because we know that vector product is non-commutative. So if we change the vector order of A and B, we can change basically the order or the position of lambda, but not A and B. Okay, now the next thing, we will see the expression for the vector product in component form. So now if our vectors A and B are written in component form as A1i plus A2j plus A3k and the vector B as B1i plus B2j plus B3k, then their cross product is given by this expression, determinant of, it's a 3 by 3 determinant basically, whose rows are I, j, k, A1, A2, A3, that means the components of the first vector, and next row or the third row is B1, B2, B3, that means the components of the second vector. So it's a very nice result to remember that cross product of A and B will be a 3 by 3 determinant in this form. And why it is so? It can be easily calculated if we just write the vectors in the component form and calculate the cross product. So A cross B is A1i plus A2j plus A3k cross B1i plus B2j plus B3k. Now let us perform the multiplication term by term. So if we take this A1i from the first bracket, A1i, and we multiply with the first term in the second expression B1i, so we will get A1 B1 I cross I. But what is I cross I? You remember from our one or two previous slides, I cross I was 0. So this term vanishes. The next one, A1I cross B2J. So we will get A1 B2 I cross J. And what is I cross J? If you again remember from the observations we have seen, I cross J is equal to K. So the first term we now get after the multiplication is A1 B2 K because I cross J is K. The next term is going to be A1I cross B3K. So the scalars are A1 B3 and the vectors what we multiply we get here I cross K. Can we tell what is I cross K? Now again remember that we had written there K cross I was J. So I cross K, because vector product follows the anti-commutative law, so that is going to be minus J. Now, very similarly, if we proceed with the term by term multiplication like this, we will get the next terms. So finally, if we just rearrange the terms, taking say I cap as common, the coefficient here is a2b3 minus a3b2. Then with j we have this minus a1b3 minus a3b1, and with k we have a1b2 minus a2b1. So is it not the value of this determinant if you look carefully? How do you get the value of the determinant? I hope everybody remembers. What you do, I over, if we do the multiplication starting with the elements of the first row, so with I over here, we do this cross multiplication a2b3 minus a3b2. So this is this term. J, but with j we take a minus sign and then cross multiplication a1b3 minus a3b1, and with k a1b2 minus a2b1. So this shows that a cross b is given by this determinant. And now the last thing to talk about in this vector product is the geometrical interpretation. So what we see here now is a very interesting result, that if the two vectors a cross a and b represent the adjacent sides of a triangle, then the area of the triangle will be given by half modulus of the cross product of a and b. So half mod a cross b. How it happens? Let us see. If we just see this figure, then only we can understand this. So suppose we have the two vectors a and b, which represents the sides AC and AB of the triangle ABC. Now, what is the area of a triangle? I hope everybody remembers the area of a triangle is given by half base into altitude. So therefore, half base is this AB and altitude or height is this CD. Now this AB, as per our figure, this is the vector B. AB vector is the vector B. So this length AB, this is nothing but mod B. And what is this CD? If we recapitulate our knowledge of trigonometry, CD will be given by AC sine theta, or rather mod A sine theta. So therefore, by using this formula of half base into altitude, area of the triangle ABC becomes half mod A mod B sine theta. So is it not the magnitude of the cross product? So finally what we get is area of the triangle is half mod A cross B. One more result, but which actually follows from this only, that is the area of a parallelogram now will be given by just mod A cross B. If we have understood the previous result, we can easily understand this. So now suppose we have two vectors A and B which represent the two sides AD and AB of the parallelogram ABCD. So area of the parallelogram, I think we remember that it is base into altitude. So now just as before, AB multiplied with DE, and base in this case is B, and the altitude is once again mod B mod A sine theta. So finally it's mod B mod A sine theta and nothing but the modulus of A cross B. So that is all for the vector product. In the next class, we will talk about product of three vectors, or what we call triple product. So thank you very much and goodbye.